Assalamualaikum and hello to everyone. In this video lesson, we will continue for part 1 of chapter 3. In this video lesson, we will cover the remaining steady flow devices for subtopic 3.3, and like in previous videos, the objective for this subtopic is on the right of the screen. Now, let's look at the fourth steady flow device called diffusers. Diffusers are used to decrease the velocity of fluid by increasing its pressure. Basically, diffusers are the opposite of nozzles, and like nozzles, there are no work interaction for diffusers, meaning that work input and work output can be neglected from the steady flow energy equation. Other possible conditions are diffusers can also be adiabatic, and depending on the question, potential energy can often be neglected. The figure given is the schematic diagram for a diffuser. Now, let's look at an example on how to use the steady flow energy equation for a diffuser. For this example, we will consider an adiabatic diffuser and potential energy will be neglected. Remember to write the conditions from the question before applying the SFEE. Start with writing the general equation for SFEE and then cancel the terms based on the conditions. Now, rewrite the remaining equation. Now, since the mass flow rate is the same, we can cancel both terms. And to determine inlet velocity, we can rearrange the equation as follows. As you can see, this is only an example on how to use the SFEE for a diffuser. Now, in the SFEE, there is the term for specific enthalpy H. Just like previous devices, the values for specific enthalpy H will depend on the type of substance. For water or R134A, the values for specific enthalpy is read using the property table. For gases, the term for specific enthalpy is replaced with its related specific heat CPT. Now, let's look at the first example for diffusers. Feel free to pause to read and understand the question properly. For step 1, please try to draw and label the schematic diagram. Label the inlet as state 1 and exit as state 2, and as mentioned in the question, we can also label for the amount of heat added to the system. For step 2, to find the exit velocity, we will use the conservation of mass principle by expanding the equation, and from the equation, please note the relationship between inlet area and exit area. To determine the mass flow rate, we cannot use the mass flow rate equation because we do not know the values for inlet and exit area. Therefore, to solve for mass flow rate, we will use the SFEE because why? Because the term for mass flow rate is written in the equation. But first, remember to identify and write the conditions for the system based on the question. From the general equation, cancel the terms based on the conditions and rewrite the equation. Rearrange the equation in terms of inlet velocity. And here we can solve for the amount of mass flow rate m dot. For step 3, determine the required properties at each state. Now, since the substance is R134A, we will use the property table to determine the required properties. Now, like previous examples involving water or R134A, when reading the property table, make sure we determine the phase at each of the state. So for state 1, it was mentioned in the question, the phase is saturated vapor. So by using the appropriate table A12, we can read for specific volume and specific enthalpy at state 1. For state 2, when we compare the temperature at the exit 40 degrees Celsius with the saturation temperature table A12 for 700 kilopascal, we can see that the phase of the substance is in the superheated region. Therefore, by using table A13, at the corresponding pressure and temperature, we can read for specific volume and specific enthalpy at state 2. Now, for step 4, from the conservation of mass principle, substitute the relationship for inlet and exit area given from the question. Since both sides has the term A1, we can cancel and therefore we can solve for the exit velocity. For mass flow rate, substitute the value into the SFEE and solve for the equation. We can see here the answer for mass flow rate is 0.2984 kilograms per second. Now, let's go through the second example for diffusers. Feel free to pause to read and understand the question properly. For step 1, please try to draw the schematic diagram and remember to label the inlet and exit states. Also label the amount of heat loss from the system because this is mentioned in the question. For step 2, to find the exit temperature, since the substance is a gas, we will use the SFEE. But first, remember to identify and write the conditions for the system. From the general equation, cancel the terms based on the condition and rewrite the equation. Since the substance is a gas, we must replace H with CPT, and from here we can solve for temperature at state 2 in step 4 later. To find for the density of air, we will use the ideal gas equation. For step 3, determine the required properties using the required ideal gas laws for state 1 and state 2. As we can see, for state 2, there are no properties which are required, so we can proceed with step 4. For step 4, substitute the required values and solve for the question. So for exit temperature, we can see here in Kelvin, 415.94 Kelvin. However, in the question, it wants the answer to be in degrees Celsius, so we have to convert it into degrees Celsius. For density, using the ideal gas relationship, we can see that the density for air is 1.26 kilograms per meter cube. And for exit area of the diffuser, the answer is 0.03311 meter square. Okay, we have come to the fifth and final steady flow device, and it is called the throttling device. Throttling devices are flow restricting devices used to reduce the temperature and pressure of a flowing fluid. There are no work interaction for a throttling device, meaning that work in and work out here can be neglected. Other possible conditions are, it can also be adiabatic, and depending on the question, we can often neglect kinetic and potential energies. Now, let's look at an example on how to use the SFEE for throttling devices. And this example is based on adiabatic conditions, and kinetic and potential energies will be neglected. Remember to write the conditions for the device. Start with writing the general equation and cancel the terms based on the conditions. Now, since the mass flow rate is the same, it can also be cancelled. So, as we can see in the final equation here, the enthalpy at the inlet is equal to the enthalpy at the exit. The values for enthalpy here are based on the substance. So for water and R134A, the values are read from the property table, and for ideal gases, specific enthalpy H here is replaced with its respective specific heat relation CPT. But however, throttling devices mostly involves substance in the form of liquid, so therefore we seldom see application for throttling devices which uses gases. Now let's look at an example for throttling devices. Feel free to pause to read and understand the question properly. Please try to draw the schematic diagram in step 1 and label the inlet as state 1 and exit as state 2. For step 2, since the substance is steam, which is a byproduct of water, we will use the property table to find the temperature at state 2 as mentioned in the question. However, when we look at the properties which are provided in the question, there is only one property at state 2, and to find the second property, we must apply the SFEE. So write the general equation and also don't forget to write the condition for the system. So from the general equation, cancel all the terms based on the condition, and from here we can see that the mass flow rate is the same, and finally we get the equation H1 equals to H2. So the enthalpy at state 1 is the same as enthalpy at state 2. So when we do step 3, at state 1, we have to read for the enthalpy, and using the value for enthalpy at state 1, we can determine the temperature at state 2. So for step 3, at state 1, determine the specific enthalpy. Remember to check for the phase. So at table A5, 8000 kilopascal, when we compare temperature at state 1 to the saturation temperature, we can see that it is greater, therefore the phase of the substance is in the superheated region. So by using table A6, at 8 megapascal, 350 degrees Celsius, we can read for the value at H1. And using this value for H1, at state 2, at a pressure of 2 megapascal or 200 kilopascal, we will compare, using table A5, 2000 kilopascal, we will compare the value for enthalpy with the value for Hg. So as you can see, the value for enthalpy at state 2 is greater than the value for Hg. Therefore, the phase of the substance is in the superheated region. So using table A6 at 2 megapascal with the value for enthalpy H2, we can see that it requires the interpolation technique to find the temperature at state 2. So doing the interpolation technique, we can see here that the temperature for state 2 is 285.07 degrees Celsius. For step 4, since we have already solved the question, step 4 is not required here. We have come to the end of today's video lesson, and also we have come to the end of part 1 for chapter 3. Please refer to the original notes for exercises. If there are any questions, please comment in the forum section. Thank you for your attention and have a good day.